Hello guys, today we're starting a new series on Zcash, and we're taking one aspect of the cryptocurrency and analyzing how it works. Today we're taking a look at diversified addresses, and so this is a feature that is not unique to Zcash, but very useful and I think a little bit underused. All right, so let's get started. Like every cryptocurrency, accounts are represented by addresses. You send coins when you send coins to somebody. You send coins to an address, and an address is a string of characters. For Bitcoin, it's the string of characters represents a hash value, so 20 bytes. For Zcash, the address is longer and it contains 43 bytes instead. So we're talking about shielded addresses, of course, here. So we're talking about an address. What we have actually inside is it's two things. We have something called D, diversifier, and then we have something called PKD. Okay, so these are two components of the address. And the address is essentially one followed by the other. The first one is 11 bytes. Then the second one is 32 bytes. So for a total of 43 bytes. So addresses, as I said, are longer than Bitcoin because Bitcoin is 20 bytes, so it's more than twice as long. When you take a look at an address and you send coins to it, the fact that it has this D is where the diversification comes from. It means that for a given decryption key, a given secret key, you can have a multitude of addresses that are all different, but they are all decoded by the same key and under the same spending authority. So before you can actually spend something, you need to be able to decrypt the outputs. When somebody sends coin, it creates a series of outputs, one or more outputs, and for you um, to receive to decode that output, you need to be able to generate the decryption key. So the principle is that all the nodes are encrypted with a key. The key is K. And to decrypt that node, you need to have K. You need to have the same value. The encryption and decryption is symmetric. It uses the same key. But the sender and the receiver, so the sender is the person who pays you, and the receiver is you, we do not have the same information. We have different keys. And even though we have different set of keys, they are going to be used to produce the same value K. Every time you create an output, a node, you're going to create and code it with a different value of K. This encryption key is always going to be different. So how is that going to work? With the address that you have, this DPKD, there's a hidden value, or the value that only the receiver knows. That's called the IVK. IVK stands for incoming viewing key. This key doesn't let you spend the funds, but it lets you decode the output. Right? It lets you figure out the K. So this is a value that only the receiver has. The guy who creates the transaction does not know IVK, but he has to be able to create to get to the same value K, so that the receiver can use his IVK to decrypt. So the process is very common. It's in shielded protocols. HTTPS is using the same technique, and it's called key agreement. So the idea here is that sender and receiver must agree on the same value of the key, even though they are not in communication directly. And that protocol is called key agreement. And the technique was invented by a couple of guys, Diffie and Hellman. So it's called Diffie-Hellman. DH for short. So let's see how it works. You know that, or you, I hope you know, right? That when you have a secret key, so any secret key um, can be turned into a public key by multiplying by a generator point using if we use elliptical curve cryptography. Elliptical curve cryptography essentially uses a curve. So this is a curve for Bitcoin, but other cryptocurrencies have different curves. And on that curve, you have points. The points in blue. And there's a way to add points together. And by the fact that you can add points together, so you can add this point and this point, for example, and then you get another point. It means that you can also double the point by adding it to itself. And by repeatedly adding a point to itself, you can define the multiplication of a point by a value by integer. Saying, for example, that 3 times g, let's call this point g. 3 times g is g plus p plus g. So once you have a secret key like IVK, you can multiply IVK by g by saying that, for example, if IVK is 3, then 3g is g plus g plus g. IVK times g is g plus g plus g. Of course, in practical usage, IVK is going to be a very, very large value. So that the product of IVK by g is not going to be something that is easy to find. And here's the whole point of elliptical curve cryptography. Once you multiply a point by a value, the resulting point, let's call it P, is such that knowing P and knowing G doesn't let you find the IVK. So that's something that we have to assume because it's very, very hard to prove. So once you have that, the idea behind Diffie-Hellman is that the sender is going to generate its own random value. So it's going to be a ephemeral secret key, a secret key that he's going to pick randomly just for the sake of this particular output. And we're going to call that secret key ESK for ephemeral secret key. Then he can derive an ephemeral public key, we call it EBK, by multiplying ESK by G. So again, he's the only person who knows ESK. The receiver has no idea of this happening. Once he does this, he's gonna put in the transaction, so the transaction has an output, and then he's gonna put in there EPK, so 32 bytes, so that the receiver can know the EPK. He has EPK, and then he has the encrypted note. EPK is going to be transmitted in clear inside the output. Right. So now, if you are the receiver, what you can calculate is so this EPK, which is a point again, right? And you multiply by IVK. So, okay, so this doesn't really look like a point. So I'm going to use a better notation. I'm going to make this guy. Capital T. Yeah, put E for ephemeral. So I multiply IVK by my EPK. And if I expand this, I can expand this as IVK times ESK times G. It's just the definition of IPK. And if I swap these guys around, because this is just a multiplication of two integers, I can swap this around as ESK times IVK times G. And then I recognize that IVK times G is my point. My point here. So what I've proven is that if the sender uses his ephemeral secret key and he multiplies by PKD, so this is PKD again, right? PKD. He gets a point. So let's call it B. Or let's call it K. So this is our K. He gets a K, and if as a receiver I use my secret key IVK and I multiply by EPK, this guy here, I also find K. So there are two ways to find the same value K. If I'm the sender, I can find K by multiplying the PKD, which is part of the address, so I know that, because I know who I'm sending the coins to. And I take that value, PKD, and I multiply by my secret ephemeral key. I get a value, okay? And the receiver, who does not know his ESK, but he knows IVK, he takes IVK and he multiplies by EPK. EPK is part of the message, so it's also public. He would find the same value, right? We have K here and K here, the same stuff. So both guys, both sender and receiver, are able to find the same value of K in order to do the encryption and decryption, but nobody else can, because both of these guys, either the receiver or the sender, have access to a secret value. For the sender is the ESK that he has chosen himself, and for the receiver is EVK that he knows because this is a value that he used to derive PKD. All right, so two ways to find the same value, and nobody else can get access to K. And at no point was either sender or receiver exchanging or transmitting the secret, one of the secret keys. So this protocol is absolutely secure because only the public data, in this case either PKD or EPK, were transmitted in clear, stored on the blockchain. So that's the idea behind the key agreement. Once you have K, then you can run the encryption process and the decryption process. So, but then you may ask, okay, all of this is all great, but where is diversification coming from? Is there any diversification? And diversification comes from the fact that as the guy who creates the address DPKD, I can choose G as I wish, as long as this relationship here stands. If I say that PKD is equal to IVK times G, then I can do the rest. Right? And the trick is that I choose G the way I want it. If actually G was fixed and G was agreed on by everybody, then I wouldn't have to publish D, right? I would just publish my PKD. But the trick here is that the D that I'm putting in my address allows me to relate, allows me to the sender and the receiver to associate a particular point G. So there's a way to choose to find this point G based on D, and this is documented by the protocol. Right? Whenever you choose an arbitrary D as diversifier, then from that D, the protocol, there's an algorithm to derive G of, and it's actually now G of D, right? Because now D is a parameter. So everything else remains the same. The only difference is that you start by taking D, part of the address, and the sender has to figure out what is the matching point, the matching generator point. Then, if the receiver wants to create another address, then he would choose another value of D, any value of D of 11 bytes, that can be associated with a point on the curve will be a suitable value for the generator point. Once he has this GD, he multiplies that by IVK to generate the PKD, and then the PKD becomes part of the address. So again, that the address is always a combination of the diversifier and the public point that matches that given diversifier for his secret key IVK, incoming viewing key. So that's the way it works. And the advantage of having this system is that as you generate more and more addresses, if for example you have an account but you want to have 1,000 different addresses, because then when somebody pays you, you can identify that this address was, let's say, used only once for that particular invoice, and then from the address you can relate the particular invoice with the address. You can do that without creating different accounts. They're all going to be under the same decryption key, the same IVK. And the obvious advantage of that is that when you try to decrypt the notes, when you see all the transactions going on the blockchain, and you try to find out which ones are your payments, you are obligated, you must try every decryption one by one. There's nothing that marks the transaction output as being yours. The only way for you to know that's yours is to attempt to decrypt it with all this stuff. You have to run all these algorithm with the point and everything. But if the output was not encrypted with the IVK, was not using IVK, so the note is actually for somebody else, the decryption will lead to garbage, will lead to a series of bytes that makes no sense. That no, of course, there's a checksum. There's a way to see if the decrypted message is valid. Therefore, you can recognize that this is not for you, but you have to try. And if you have 1,000 addresses that all have different IBKs because they all are unrelated to each other, because you created 1,000 accounts, then you have to try the whole process here 1,000 times, and it's very intensive. It's not like a simple process that you can see here. Therefore, if instead you use diversified addresses, you would use a single IBK, and then you decrypt all this stuff, and then the note that you get at the end, the decrypted note, will tell you what D was used. And then you don't have to basically go through 1,000 decryption. This one attempt at decrypting is worth 1,000 decryptions. Therefore, your decryption process is 1,000 times faster. There are wallets, there are users who are not familiar with this mechanism, and they created a new shielded address every time they make a transaction. At the end of the day, they had thousands of different accounts, different secret keys and different IVKs. And after that, their wallet was basically unsynchronizable. It would take too long to figure out which transaction was theirs. So there's a drawback though. The fact that all these keys, all these addresses are under the same key means that all these payments are going to be under the same spending authority. The same secret key will be able to spend from any of these accounts. So at the end of the day, if all these accounts are really logically different and you need to have different authorities to spend, for example, they are actually held by different people and they want to be in charge of spending, then using diversified addresses will not work, because the IBK here is the same, and they all can be decrypted with the same key. That all the accounts are basically merged into one. But for any other reason, if it was just for convenience or just for obscuring the relationship between these addresses, so sometimes you want to give different addresses because you are giving the address to different people, and you don't want these people to relate the address. So if that's the reason why you're doing that, you're giving different addresses, then instead you should be giving diversified addresses. All right, so that's the story behind diversified addresses. That's it. All right, enough for today.